All right, guys, let's dive a little bit further into the structure of alkanes. We're going to talk about rings and about Sis Trans Isomerism today, which is going to be a big topic for us pretty much all year long. So typically when we look at cyclic alkanes, and we look at them when we draw them out, we kind of draw them as these little flat structures. And so in some cases that's relatively accurate. So if we look at a cyclopropane molecule, okay, it sort of looks, pretty flat, and that kind of makes sense because any 3 points define a plane. So a plane would be the 3 carbon molecules, okay, and then of course we've got our dash wedges there to show that the hydrogens are sort of coming in and out. But if you notice as you look at this, the bonds are a little strained. I mean, the normal bond angle that we want is 109.5 degrees from a tetrahedral carbon. And of course, these are, I mean, if we're talking bonds like this and it's essentially forming a triangle, those are going to be 60-degree bonds. And so you can tell there's a fair amount of strain there. And so that makes this a somewhat unstable molecule. Not unstable in the sense of it doesn't exist, but I mean that it would like to react and it would sort of like to find something to happen to relieve that strain. And what also makes cyclopropane a little bit unique is that it's sort of the last of our flat cyclic molecules. Once we get past cyclopropane, the molecules themselves don't remain flat any longer. And I'll sort of show you what I mean here as we go along here. So I'm going to make a cyclobutane, okay, which obviously is our next thing here. It kind of looks like this. Now if you look at it in the picture there, or even if you look at the one that I've got constructed here, the one I have constructed is a little hard to tell on, but it's not exactly perfectly flat, okay? What you really have are you sort of have 3 carbons in a plane, and then 1 carbon is just tilted up just a hair. And you can see that in this diagram. And again, you've got some angle strain and some ring strain here that's just going to force this so that they're not quite in the normal plane. Cyclopropane is the last time that you'll see one of those cyclic alkanes where everything is perfectly flat. And so what happens if we go up another step? What if we go up to cyclopentane? We're going to talk a little bit more about cyclopentane. We talk about cis trans isomerism here as well. Okay, and so what we've got there is if we make that molecule is that it essentially looks kind of like this. And you'll again notice that you've got 4 of the carbons more or less in the same plane here. Okay, but this carbon over here is poked up a little bit, and that's the same thing we see here on the video. You got 4 carbons somewhat in the same plane, and then another carbon sort of poked up out of the plane with its hydrogens up there. Okay, so that obviously is going to mean that the bigger we go, sort of the more strain and the more different sort of shapes we can have. Now, what we don't have in this case is we don't have any carbon-carbon bond rotation, because even though these are single bonds, they're pretty much locked into place. I mean, I can't really rotate anything around here because I'm not just bonded in 1 single bond, I'm actually bonded in 2 single bonds. Cyclopentane is an important case, and what's another really important case for us is cyclohexane. And as we see cyclohexane, this is where we're going to start to really see some different conformations. Now there are some for the others as well, but cyclohexane is where they're really going to become important for us, and we're going to see them over and over, not just in the organic part of class, but as we get to the biochem part of class too, and we talk about glucose and those sorts of molecules, we're talking about 6 carbon rings, and so we're going to see the same basic sort of structure from those. So this is a cyclohexane molecule. You'll notice that it looks like it's drawn really weird, and the way we've sort of typically been drawing these is that we've been drawing them to try to kind of keep them as a hexagon. Well, that hexagonal shape actually doesn't work. I mean, it just doesn't. The bonds aren't able to stay in that shape. There's too much pressure on them. And so what actually happens, sort of the most favorable state for a cyclohexane molecule is going to be this guy here. You see we've got a 6 carbon ring, okay? So we still have our hexane, okay? We still got the 6 carbon ring there. But instead what is going to happen now is that we're kind of in this formation where you can kind of picture this as a chair or maybe as a chaise lounge. So you got like the back of it here, and then you've got the actual chair part and then the foot of it down there. Again, we see that same sort of deal here, back of the chair, part that you would sit on, and then the foot of the chair sort of hanging down. That is our stable, sort of traditional conformation that we want cyclohexane to be in. What you need to note about this is the way that the hydrogens are positioned around the ring. We have these things called axial hydrogens, and the axial hydrogens are the ones that are poking up okay, that are basically perpendicular to where the plane of the ring would be. So you get 6 of those. So we got 3 on the top and 3 on the bottom sticking down. And then we have what we call equatorial hydrogens, which are the ones that are sort of going around and sticking out of the side or the equator of the molecule. We got 6 of those as well in a cyclohexane molecule. Okay? Now, that is not the only possible conformation of a cyclohexane. First off, we can actually flip this. So if we sort of flip these around, what I can actually do is sort of twist these atoms so that the other ones become the axial ones, and then we'll get some of the other ones to come up to be equatorial. This is called a ring flip, okay? And it's definitely possible and does happen. And so when we get this completed, and I didn't quite do that one right, basically every other one, again, is going to be axial, and then every other one is going to be equatorial. Okay, and so that's called a ring flip when that happens. But the other actual normal conformation that we're going to see of cyclohexane is we're going to see that we got the chair conformation that we have here. And then what we could also have is what's called the boat conformation. And what happens then is that instead of, you know, one end sloping down and one end sloping up, we've got both ends sloping up, okay, to make sort of a little boat-like structure like you see here. Now, as you look at that, you sort of imagine that molecule, you can kind of immediately tell that that's probably not going to work real well, that that's not going to be stable from what we learned about conformers in our last thing, because I've got a bunch of stuff up top, all going to be causing some interference with each other. And so that conformation is not going to be as stable as the chair formation would be. Possible, okay, just not quite as stable. So what we really like it to do is to go down and be that nice chair module rather than we would the boat. Okay, so just when you're putting rings together and you're looking at them, you want to think about the conformation, think about how the angles are stretched. You know, theoretically speaking, in this case, you know, our angles here are much better because our angles between the 3 carbons here are going to end up to be like 120 for each, which still isn't ideal. We want 109.5, right? Well, that's exactly what happens when we do the chair conformation. We don't get exactly 109.5. I want to say it comes out to be something like 111, but it's a lot closer to the natural tetrahedral bond angle rather than that 60-degree thing of that cyclopropane where everything was just sort of jammed all together. Okay, so that's conformations. That's the ring structures. We talked a little bit about their stability. Let's talk a little bit about Sis Trans Isomerism. I'm not going to go too deep into this right now because when we do alkanes and alkenes, or alkenes and alkynes in the next unit and talk about naming of those, we'll get a lot deeper into it than what we're going to do right now. But essentially, if you've got a ring structure, and we say that we can't rotate, you know, just simply rotate around one of the bonds. So I'm back to my cyclopentane here, okay? And don't let the fact that it's there's no E on the end of it bother you. There should be an E. That's a different language translation. You see it's pretty similar, but not quite the same. Okay, so cyclopentane. And what we're going to do is we're going to put 2 methyl groups on that pentane. So basically I'm going to take 2 of my hydrogens that are next to each other, okay, that are on 2 carbons that are adjacent to each other. Okay, you see that in the drawing here. And I'm going to show 2 possible scenarios. One of those scenarios is that I take a couple of methyl groups and I pop them on there, okay, and they're on the same side of the ring, okay? So think of the ring. You've got like a flat plane here, and again, we know it's not perfectly flat, but you got a plane there where the ring is. And if the 2 groups, the 2 substituents, in our case of methyl groups, if they're on the same side, we call that cis isomerism, okay? Conversely, if we sort of switch that around and we took one of them, we took one of them and popped it over to the other side, still attached to the same carbons, okay, so we haven't changed the structural isomerism. We're still attached to the same carbons. But now it's going on the other side of the ring, okay, and that is what we call trans isomerism, okay. So cis means they're on the same side, and trans means they're on opposite sides. So cis here, trans here. This is going to be super important to us because this has a lot to do, as we talk about alkenes and our bigger molecules later, this has a lot to do with their reactivity. They just don't react the same way if they're trans or cis. They're not quite the same molecule. Even though they've got the exact same atoms, even though they're bonded at the same places as each other, the fact that they're cis and trans means that you've got more space on some ends, and so more ways for things to attack, not really attack, but to bond to. And so that, therefore, is going to lead to some different structures. So just real quick, and I'm not going to go deep into this because, again, we are going to get into it. If we've got an alkene, okay, where we've got a double bonded structure, and real quick, let me just draw that up here for you. I'm going to draw a butene, okay? I'm going to draw two butenes. So I'm going to draw carbon, carbon, double bond. That's what makes it a butene, carbon, okay? Picture your hydrogen sort of all around that. Well, there are a couple of different ways that we could draw that we could actually make the structure of that molecule. Okay, so the way I have it drawn makes it look like it's all sort of just in one line. But that's not actually the case. I mean, what actually would be the case is that we could have the methyl groups that are on the end, okay, so the two end carbons, they could be on the same side as each other. Okay, so let me draw that for you. Grab the little eraser guy here since I got enough problems drawing as it is. Okay, so if I grab my pen here, I could draw the methyl groups down here, and remember, these aren't just carbons, these are methyl groups. Okay, I'm being lazy. If they're on the same side of the double bond, then that is cis isomerism, and so we would call that cis-2-butene. Okay, or we could draw them on opposite sides, in which case it would be a trans butene. Okay, so that's a cis trans isomerism. Just know what it is. We'll do a couple of practice problems, but we're going to dive a whole lot deeper into that whole cis-trans concept when we get into alkenes and alkynes, multiple bonds on our carbons, in the next unit. So let me real quickly just summarize the isomerism that we've learned so far. Remember, isomers mean that you have the same number, or the same type and number of atoms. Okay, so you got a C5H12, a pentane, but there's a whole bunch of different ways that you can arrange those carbons and hydrogens around each other. So what we did when we talked about stuff in the first unit is we did structural isomers, meaning that there was a different bond pattern. Okay, meaning that the connections between the atoms was actually different. They didn't connect to the same atoms at all, and that's what led to a lot of the branching stuff. And so you could have a straight chain pentane, or you could actually have a 4-chain with one branch hanging off of it, so you could have a methyl butane, and it would have the same formula as that straight chain pentane. So that's structural isomers. What we've learned about starting in this unit is something called stereoisomers. Stereoisomers means that they have the same bonds, okay? The bond pattern is the same, the bonds are in the same place, but the molecules themselves can be different. They can be different in a couple of ways. The first way we learned in the last video was that we could rotate around a single bond. If we rotate around a single bond to get the eclipsed or the staggered molecules, so we'd have to use the Newman projections. Those are what we call conformers. Okay. And then one of the things we're going to deal a lot with as we go through the rest of the year, what we call configurational stereoisomers, which means you can't convert them by a single bond rotation. If we look at this butene molecule that I've got here, I can't just twist this to make it go between cis and trans. That double bond there holds it basically into place. It locks it into place. I can't twist it like I would if that was a single bond. If this was the single bond like we had in butane in the previous video, no problem. I just flip that around. Okay, and so that would get me back to my axial or my staggered shape there, or my anti, not my axial, staggered shape, as opposed to the eclipsed shape. Now, in this way, if I'm cis, I'm pretty much locked into eclipsed. Okay, whereas if I jumped back over to my trans, then I am basically locked into my anti or my staggered shape. Okay, so once you get those double bonds in there, or once you have a ring structure, okay, you can't just flip them around anymore, so you don't really have conformers in that normal sense of just rotating the bond as easily. Okay, and so that's going to lead us into cis and trans isomerism. We'll also see later that's going to lead us into some other forms of stereoisomerism as well. All right, thanks a lot, guys.